I want to talk about the average value of a function on two variables, but I thought we'd start by talking about the average value of a function on one variable. So in your Calculus 2, you likely saw this formula for average value. And if you didn't, there it is. I'd like to talk about that value, this calculation, two different ways to justify why it finds the average value. And one's kind of hand wavy and depends on area in this picture, and the other is actually a derivation. And then I want to take that up a dimension to functions on two variables and do the same thing. Talk about the kind of look at the picture, hand wavy explanation, and then the actual derivation. So the intuitive way of looking at this is this calculation tells me an area. This b minus a on the bottom here is a length. And so if I think about that, I'm taking an area and dividing it by a length. And I could think about that as telling me the height of a rectangle that would have the same exact area as this function, which I could imagine being here. So this rectangle I'm drawing, I'm claiming, has the same area as what's in red, making this the average height of the function, right? Those rectangles match up, so the heights must average out. All right, so that's the intuitive understanding of what that average value is doing. Let's actually see a derivation now. And see, the idea is we could approximate the average value by just taking a whole bunch of y values and adding them together, and then dividing by the number of y values I chose, and I'm going to think about that as multiplying by 1 over n. So it's like I choose some places on the x-axis, and x1 and x2, just a bunch of them, and I calculate some y values. And I add those y values together and I divide by the total number. And of course, if I take more and more y values in there, I get a better and better estimate for the true average value. Well, this is a sum from 1 to n of f of x sub k times 1 over n. And that would approximate the average value. But it should tend towards the actual average value if I take a limit as n approaches infinity. And this is starting to look an awful lot like a Riemann sum. It's not quite a Riemann sum yet because it doesn't have a delta x in it. So I want to figure out how to get a delta x in it. So if I thought about, instead of just taking sample points, first dividing up the x-axis into subintervals of equal width, and then letting these sample points come from those subintervals, then I would have a delta x equals b minus a over n. Okay, so delta x equals b minus a over n. Well, if I divide everything by b minus a, that means delta x divided by b minus a is 1 over n. So that's going to let me sneak a delta x in here by thinking of that 1 over n as a delta x over b minus a. That lets me write down the equation. The average value of f is equal to the limit as n approaches infinity of the sum from 1 to n of f of xk times delta x over b minus a, which I'm just very quickly going to rewrite as delta x times 1 over b minus a. 1 over b minus a would be a constant, so I can pull it out front of my sum, and I can pull it out front of the limit as well. And now what I have is the actual Riemann sum for the integral of f from a to b. And I'm going to reimagine this just one more time. This is the formula for average value you know, and it's absolutely true. But one way to think about it is that it's 1 over the length of the subinterval. Not subinterval, the length of the whole interval between a and b, times that single integral. And that seems pretty funny to write since that's such an easy calculation, but I'm going to leave it there because it's going to look familiar to us in a moment. So now I want to think about the average value of f of x, y over a region R. So I think about a region R in the domain. So here's my region R. And I'm imagining some function. I'm going to imagine a positive function. One of the powers in the derivation we just did is it doesn't actually depend on this being a positive area, right? It would work for positive quantities, negative quantities, because we were just adding up a whole bunch of y values to start with, and we end up with a definite interval. So that's really the power there, but just for convenience, I'm imagining this being a positive function that's over this region. So one idea would be to find the volume under the surface over that region and divide it by the area of the base in the plane. Because a volume divided by an area, well, that's cubic units divided by square units, it's like it would give you an average height. How high to draw a cube, right? Just dragging this straight up, or to make a prism that would have the same volume telling you an average height above the region, which would lead me to think that the average value of my function on two variables would be 1 over the area of R times the volume. So the double integral over R of f of xy dA. So I claim that this is the corresponding average value formula for a function on two variables. Then instead of dividing by a length, we're dividing by an area. Well, that makes sense, right? The formula here, we're integrating over a length and we're dividing out the length. Here we're integrating over an area and we're dividing out the area. But let's make sure we can derive this using the same kind of logic. So I want to imagine that I divide this region up using rectangles of equal area this time. What that would mean is every single one of those little areas would be the total area of R over N. But I'm using areas of equal width. Well, then in each one, I pick a sample point, doesn't matter which one, and I compute a whole bunch of z values. So I have a f of x1, y1, plus an f of x2, comma, y2, plus dot, 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 plus f of xn, yn, and then I divide by n. Well, I think you see what's going to happen next. This is a sum that's going to look a little bit like a Riemann sum. So this is the sum from k is 1 to n of f of xk, yk, all times 1 over n, because I could imagine distributing that through to every term. And that would let me write down that the average value is approximately the average value of that function on two variables is approximately that sum. Okay, well, I can make that inequality by taking a limit as n approaches infinity, and then I have the realization this isn't quite a Riemann sum, but it's real close. And I'm going to do the same kind of trick. I have delta A is equal to the area of R over N. So if I divide everything by the area of R, I have 1 over N equals delta A over the area of the whole region. So I'm going to replace this 1 over N with delta A times the area, over the area of R. Well, 1 over the area of R is a constant, which I could bring out front of both the sum and the limit. The area of R. leaving this as f of x, xk, yk, delta a, which is this double integral. And here we have the formula for the average value of a function on two variables.